Hello and welcome to the Daily Space for today, Tuesday, September 8th, 2020. I am your host, Dr. Pamela Gay, and I am here to put science in your brain. Today is going to be pretty much a single story day because the story we have is big enough that we need almost an entire episode to really explain it. This is the story of the discovery of an intermediate black hole with a mass of roughly 142 solar masses that formed via the combination of a 65 and 85 solar mass black hole. Now, I know some of you are thinking, we know there are supermassive black holes that are millions and billions of solar masses. Why is 100-something solar mass black hole so exciting? Well, in part, it's exciting because we haven't had definitive proof of this size black hole existing. It appears that black holes can form in at least two different ways. The giant black holes in the largest galaxies that formed at the beginning of the universe appear to have formed through a massive and potentially turbulent inflow of material at the center of what would become massive galaxies, overdensities in the initial distribution of material in the universe. In this way, the first galaxies and first supermassive black holes all grew in size together. Once stars began to form, the other confirmed way to form black holes started as well. The most massive stars, well, as they rapidly fuse successively heavier elements in their cores, they eventually end up with cores that are full of iron, and energy can no longer be released in a fusion process. These stars, which may start out 20 or more times the mass of the sun, will undergo mass loss throughout their lives. And the final black hole will be as small as 3.5 solar masses, and, well, most stellar mass black holes appear to be 5 to 10 solar masses in size. The question on many cosmologists' minds, however, has been how do we get new galaxies growing and containing growing supermassive black holes in the process when these are the only two ways we've seen black holes exist, supermassive and stellar mass. Now, when we look at dwarf galaxies, the kind of galaxies we think are the building blocks of most large galaxies, we aren't finding black holes in their centers. This implies that somehow galaxies between stellar-sized and supermassive-sized have to have a way of forming and growing that allows new galaxies to form and grow around them. But we haven't seen these intermediate mass black holes. They've just refused to be found until now. We can detect black holes two different ways. First, we find them by looking for places in space where only a high-density, massive object can explain observed phenomena like accretion disks and high-speed orbiting companions. The second discovery method involves looking for gravitational waves generated when black holes form and merge with other massive objects, including other black holes. Gravitational waves are literal waves in the space-time continuum that stretch and contract everything. They contract space as they radiate through the universe, carrying with them energy lost during the merger or collapse. We detect these waves on Earth by looking for the literal changing in distance that occurs between 2 points in a massive laser system. By building multiple of these systems scattered across the planet, scientists can out the approximate direction the wave is coming from. The combined frequency and amplitude pattern of the incoming waves allows scientists to figure out the approximate sizes of the combining objects. The U.S. detectors are the LIGO systems, and since their first detections in 2015, LIGO, working in collaboration with Europe's Virgo system, has made dozens of detections and candidate detections of gravitational waves from merging black holes and neutron stars. The majority of the confirmed detections have come from stellar mass black holes with mergers of systems that are just tens of solar masses in size, while resulting black hole masses had been as great as 80 solar masses. The initial black holes had all been below the theoretical limit of 65 solar masses that is thought to be the maximum size a black hole from a single collapsing star can be. This new merger between a 65 and 82 mass black hole has two inexplicably large black holes. While a 130 solar mass star can end its life as a potentially 65 solar mass black hole, larger stars initially between 120 and 200 solar masses, are unstable and should explode and leave nothing behind. It's unclear if mass loss allows more massive stars to stay massive long enough to form more massive black holes. If this is possible, those stars would create 120 solar mass black holes, leaving a gap of no black holes between 65 and 120 solar masses. Now, that's a gap created in the distribution of black hole masses that form from single stars collapsing. For this new merger, these limitations mean that it is just on the edge of possibility that a 65 solar mass black hole formed from a single star. But that 82 solar mass monster must have resulted from a prior merger. I honestly feel this is most likely a system in which each black hole grew through the merger of two or more lower mass black holes or neutron stars, giving us the 142 solar mass, intermediate mass black hole we've been looking for. Now, it's unclear how black holes find one another across the merging generations. And we still have no clear indication of how often these mergers happen. We still have a lot to learn and observe. But now we know these mergers are happening, growing bigger and bigger black holes over time. Complicated systems excite scientists, and gravitational waves hit all the right buttons. They require amazingly sophisticated instruments. They are understood with truly complicated math. And these are relativistic systems. But as complicated as gravitational wave systems are, they're still solvable. What is not solvable is the majority of three-body systems. Systems containing three different masses of approximately the same size. Now, a new triple system has been discovered by the Atacama Large Millimeter Array, and this stunning system contains misaligned rings of dust that have the potential to form planets. This system, GW Orionis, shows three different sets of rings, with the innermost ring apparently aligned perpendicular to the other two. And all these rings are larger than the orbit of Neptune. And this is a truly massive system, with the outermost ring in this system larger than any dust ring we have previously seen. And it's thought that between that first ring and that second ring, that this change in orientation is driven by a planet that is in there orbiting with these three stars. Now, there may be other planets. What they do know for certain is they cannot dynamically figure out how to get these rings to be misaligned using just the physics of where those three stars are located and how they're moving. It takes another mass, making this an even harder to model system. Again, there's no solution for your typical three-body system where the masses aren't all that distinctly different. This is a super cool system. I'm sure we're going to be hearing more about it in the future. It is currently being published. I would like to say that the Large Synoptic Survey Telescope out at the Vera Rubin Observatory is still kind of hanging out, not being built due to COVID, but folks here in the United States working at SLAC, the giant accelerator facility out in California, have been able to test its massive camera. The camera that will eventually end up on that LSST, it's the biggest camera ever built. It has a viewing range that is capable of imaging an area of the sky 7 moons across. And it has sufficient resolution that if you were in an airplane 15 miles up with this particular detector, you'd be able to resolve a golf ball sitting in the green. Now, for reasons that I do not know and wish I knew, they tested their camera out using a pinhole camera. That part is entirely normal. This allows them to get as little light as they wish coming up through a tiny hole in an otherwise opaque substance. And the thing on the other side of that pinhole camera that they were resolving was a head of broccoli. I can't explain this. Some things have no answer. So the Large Synoptic Survey Telescope has now been used, well, not the telescope, but the camera that will someday go on the Large Synoptic Survey Telescope has been used to image broccoli. And that is all, people. That is all. This concludes the Daily Space.